Hello guys, so welcome back to our series of Sedra's problem, and also this is homework solution of 21. So this circuit is a common base amplifier in which the input is at the emitter, this node, and the output is at the collector. And again, the nodes that are not mentioned is the common one. So here is the base, which neither connected to the input or output is a common node. That's why this is a common base amplifier. Okay, so let's analyze this circuit in both DC and EC and find the parameters, the characteristic parameters of this amplifier, like AV or input or output, all such stuff. So let's start by the DC. So in DC, all the capacitors are open, and we're going to cancel the AC sources. If we do that, this circuit will be reduced to the following. It will be a very simple circuit like this. We can move RE, rotate it, so it becomes vertically like this. This is RC, and we have here RP. And this is the VCC, which is 15 volt. Okay. This current, remember, is IB. IC here. And of course, here we have IC. So we're going to assume it's in the active region, and VBE is 0.7. So we can take this outer loop here. One may say this loop is, it's not like a loop. No, it's a loop because VCC is just like a battery like this. But we usually don't draw all such stuff and just, make a node or, a point like this and put 15 beside it. VCC. In that case, it's 15. So now we have a loop. A loop. The definition of a loop, you start from one point, go to some branches, and you return back to the same point. That's a loop. Okay, so what is in that loop? We have many things here. We have IERE. This is IE, I'm sorry. We have the VBE. We have IB, RB, and we have the VCC. So from that loop, VCC, which is 15, equal to IBRB plus the 0.7 plus IERE. If we look at this equation, we know RB, of course 0.7 is just the constant, and we know RE, but we don't know IE and IB. One may say this is an equation in two unknowns. No, my friend. This is just one unknown because IE is just IB over beta plus 1. Or you can say, I'm sorry, IE is beta plus 1 IB. Or you can say that IB is IE over beta plus 1, whatever you like. So in that case, if we substitute by this relation between IE and IB, which is beta plus 1, or beta, if you just ignore the 1 to the 60, that's also valid. So if we do that, then we have one equation. Or we can say these are two equations, and you can, you can say that there are two equations in two unknowns as well. That's also valid. So if we do that, we're gonna get these numbers here. That IE equal to 9.94 milliamperes. Okay, and you can say that IB is 940 microamperes around. If you want to calculate VB, for example, VB will be, you can say it's 15 minus IB RB. Or you can say both are the same, that it's basically equal to 0.7 plus IERE. Of course, if you do both, you will find very slight difference between them, but not exact. But that's acceptable, approximation. Okay. So if you do that, VB will be 3.23 volt. If we need to calculate VC to be sure that we are really working in the active region, so VC is equal to VCC minus ICRC. This is VC here, and this is the 15 or VCC. So VC here is equal to this point minus the voltage drop across the resistance, ICRC. If you do that, of course, IC approximately equal to IE. So this guy approximately equal to IC. Okay. So if you do that, VC will be 10.58 volt. Now you can see that VBC, which is a voltage difference across the junction 2 between the base and the collector, is negative, has a negative voltage, so it's reversed by itself. So we are really working in the active region. And that's why we calculate VB and VC. Finally, we want to calculate R by or RE small in that case. Why RE small, not R by in that case? Because we can, of course, do both. R by is just RE beta plus 1 RE small. But since this is a common base, we're going to use, the special, equivalent circuit for the transistor in which we have RE small, not R by. Okay, so RE small, R by is VT over IB. RE small is VT over IE or IC, approximately, if they are approximately equal to each other. So VT is 25 millivolt, IE is known, 0.94 milliamperes. If we calculate that, this will be 26.6 ohms. That's basically the DC part of this problem. Now the AC, number 2, the AC. The AC part. First, we're going to start by the equivalent circuit. Let's draw it. We're going to start by the equivalent circuit of the transistor, and we're going to use the one for the common base. Can we use the other one? Yes, you can. This is alpha IE or IC, whatever you like. Alpha IE is IC, and you usually approximate alpha to 1. So, and this is RE small. Now is a very important stuff. What are the nodes? You have here 3 terminals. You have a terminal here, a terminal here, a terminal here. If you confuse that, the rest is wrong. So this is emitter, this is collector, and this is base. That's not enough. Where is IE small? You say here alpha IE, this is a dependent current source. So it's dependent on a current called alpha, IE, alpha is constant. We need to know where is this IE. IE is flowing in that branch here in RE. But in which direction? IE is the current flowing out of the emitter, as usual. Out of, so it will be like this. So when it comes here, it will go out like this. Okay? Out of the emitter. You can say, if this is IB, this is IC, so both are going, so one is going into the collector, one is going into the base, and both are combined and become IE, just like the DC. Always IE equal to IC plus IB, always. Now we can connect the rest of the circuit. In EC, the capacitors are short, and we can cancel the DC source, which is VCC in that case, only VCC. So what's between the collector and this is the ground? So of course this will be shorted, so it will be just a short like this. So we have just VO, there is no RL here, and RC. and this is VO. There is no RL. What is between the base and the ground? Just this resistor RB. And here is the base. Not here. Here is the emitter. This is the base now, because we are using the equivalent circuit of the common base amplifier. And again, we can use the other one. But this will make the analysis easier most of the time, or simpler. What is between the emitter and the ground? Let's check. Now the capacitor will be short, so we're gonna include now this. So we have two branches. We have RE and we have the signal. Okay, our input. Our input is the resistance that is seen by terminals of the source. So here are the terminals of the source between this point and the ground. So this is our input. You can say our input is RE capital parallel with, let's say, Rn dash. Where is Rn dash? After Re, between that point and the ground. Rn dash. So let's calculate Rn dash. Okay. So we're gonna have like another simpler circuit here. Alpha E, RC, and RE small, and IE is going up. That's very important. And we're gonna imagine, just a modeling. Imagine a VX and IX. A source giving VX voltage and IX current. So Rn dash is Vx over Ix. So what is Ix? Ix is minus IE. Look, Ix is moving this way, IE is the opposite. This is minus IE. What is Vx? Vx from that loop here equal to the voltage across Re small and Rb here. Okay. Remember, this is IB. The current flowing in Rb here. And this is IC or alpha IE, whatever you like. Okay. So we have voltage like this, and we have voltage like this. The voltage across Rb is IB is flowing from also ground to up. So it's negative. Minus IB RB. Minus IB RB. And what is the voltage across RE small? Again, it's minus IE small RE. I'm sorry, RE small. Minus will go with the minus, will go with the minus. Let's see, divide by IE small, so Rn dash equal to, if we divide by IE small, IE small, so this will be IB over IE, RB plus RE small. IB over RB is 1 over beta plus 1. Or RB over beta plus 1. Plus RE small. You can multiply, you can, simplify this. So Rn dash equal to beta plus 1. And this is RB plus beta plus 1 RE small, which is R by, The relation between R by and RE small is just beta plus 1. because the relation between IB and RE and IE is also beta plus 1. IE is equal to beta plus 1 IB, and the opposite for the resistance because it's opposite of the current. R by is equal to beta plus 1 RE small. Okay. So Rn here finally equal to RE capital parallel with all such resistance here, which is RB plus beta plus 1 RE over beta plus 1. Okay, that's basically, you know, the input resistance. Now the output resistance, which is more interesting. RO. We calculate RO by canceling, you know, any source. So we imagine there is Vx and Ix, but now it's out, and we cancel any independent source. So we cannot cancel alpha E. It's because this source here, or this one, is dependent. We only cancel independent, like this signal. So that's what we're gonna do. So we're gonna put at the terminals of the output a source, Vx, and produce a current called Ix. And we connect to the rest of the circuit by canceling any other sources in the circuit. So we have RC here, no change. We have the alpha E, no change, or IC, call it whatever. RB, no change. RE small, no change. IE, bottom up. Here is IB, bottom up. And now, when we cancel the source, we short it. So there will be short like this. So you have now RE parallel with a short. So the equivalent will be just a short. So we can just remove that. Remove that RE. That's it. So remove RE, and, you know, just make it shorter to have more space to write. Like this. That's it. But it's still a complicated one. Because of the inclusion of alpha, you don't know how much is IE. And we don't need to know. Or, I'm sorry, here we need to know, yeah. Just in this point, we need to know. But all the time, you know, when you calculate AV or, you know, GV, AV naught, R input, we usually don't need to know the current. But for RO, sometimes we need, especially if you have RE, you know, degenerate resistance between the emitter and the ground, like this case here. So let's, you know, examine this loop here. A loop starts from a point and end up at the same point. We start from the ground, we go to this point, and from this point we go to this point, and then this is the ground. So we reached up the same point again. So that's a loop. So there is a voltage here in that loop going down opposite to the current, and another voltage here going down. So RO is Vx over Ix. We're going to leave this for a moment. Let's first examine IE small. So from the loop here at the input side, which now cancelled, which is the input, I mean, you have IB small RB plus IE RE small equal to 0. So IB, or you can say IB is IE over beta plus 1, or beta plus RB plus IE RE equal to 0. You can take here IE small as a common factor. So IE small, then this will be RB over beta plus 1 plus RE small equal to 0. So you have here two terminals equal to 0. It's a multiplication of a two term equal to 0. So you have here three options. The first option is that both are zeros. The second option is, for example, IE is 0 and the second one is not 0. The third option is that the second option, which is RB over beta plus 1 plus RE is 0, and the IE is not 0. So let's examine, all options. Can IE equal to 0? We don't know. Can RB over beta plus 1 plus RE equal to 0? We don't know. Let's check. So let's start by the second one here. RB, we know its value. RB is 750 kilo ohms, so it's not 0. Beta is known, 60. And the RE small is also known. We get it. It was in the 20s or something. It was 26.6 ohms. So that term is not 0. It's actually 750 kilo ohms. It's converted to to ohms over 61 plus 26.6. So that's not a 0 for sure. That's a considerable non-negative number or non-zero number. So we left off with only options. The only option we have here is Z, IE is equal to 0. IE small is equal to 0. And if IE small is equal to 0, then this current source is open circuit. It's producing 0. A current source producing 0 current means it's open circuit. So we can just put an open here like this. Now Vx over Ix is equal to RC. So the output resistance here is RC. Good. What's also required here is GV. Number 3. Actually here RE. So GV, we know it's equal to EV, our input over our input plus our signal. But our signal here is 0. There is no R signal. If we look back here at the original circuit, there is no R signal. There is just the capacitor. So our signal is 0. So this will be our input over our input. So GV is equal to EV. So we just need to calculate EV. What's EV? It's VO over VN. Let's look at the original equivalent circuit here. VO is this voltage here, which is the current across RC, which is minus alpha IE multiplied by RC. Minus alpha IE multiplied by RC. And V input is the voltage across RE here, across that resistor, or from this point to the ground. So we can have the voltage across RE, but we don't know the current of RE. But we can do it from that loop. So the voltage across RE from that loop is equal to minus IB RB plus minus IE small RE small. So the minus go away. We can divide by IE small. So this will be, and you can consider alpha is equal to 1. That's not a problem. So this will be RC over IB over RE, RB plus RE small. So GV equal to EV equal to IB over IE is 1 over beta plus 1. Okay. So RC over 1 over beta plus 1 RB plus RE small. We can multiply by beta plus 1 in both numerator and denominator. So this will be beta plus 1 RC over RB plus beta plus 1 RE small, which is R bar, So if we do that, this will be 0.375, which is not amplification. That's basically attenuation. So yeah, you might need attenuator in your circuit, not amplification. So you might have a big, big signal, and you cannot control the source of that signal. So, and you need to attenuate it. So a way to attenuate the circuit is something like this, an amplifier also. But this is basically an amplifier with a gain that is less than 1. So instead of multiplying the input by some value greater than 1 to amplify it, we're going to multiply it by a value less than 1 so we can attenuate it. And if you remember in your function generator, if you guys go to the lab, okay, the function generator, you can control the volume or the amplitude of the output signals, and it can be less than 1 or greater than 1. That's basically amplifier. So you have inside this function an oscillator that has certain output voltage based on the user requirement. This voltage might be amplified or might be reduced. So you might have an amplifier or attenuator. Okay. Thank you very much for watching this video, and see you in the next video. Bye-bye.